From the Library of Congress in Washington, D.C.
Good morning. I'm Michelle Cattery-Bradley, a research specialist in the Science, Technology, and Business Division of the Library of Congress. Welcome to today's program, My Winter in Greenland and Summer in Antarctica, in which we'll discover the challenges faced by scientists who measure the Antarctic and Greenland ice sheets. The Antarctic and Greenland ice sheets contain 99% of the Earth's freshwater ice. History and projections of global climate suggest that the high-latitude ice-covered regions of the Earth, particularly the Arctic, have high sensitivity to climate change. Changes to these regions can profoundly affect sea level and the rate at which the Earth's climate warms or cools, placing them at the heart of research into our planet's future. But these ice sheets have recently experienced worrisome melting events. In order to understand the current state of the ice sheets and to provide predictable models for the future, scientists study the ice and conducting in situ research and will spend months at a time on these ice sheets in challenging darkness, frigid temperatures, and high winds. They must learn to solve problems of survival and transport through extreme environments while they take precise measurements with specially designed instruments. This program is the fifth in a series of programs in 2012 and is presented through a collaboration now in its sixth year between the Science, Technology, and Business Division and NASA's Goddard Space Flight Center. Our speaker today is Dr. Lora Koenig, a physical scientist in Cryospheric Sciences at NASA's Goddard Space Flight Center. Dr. Koenig has a doctorate degree in geophysics from the University of Washington. She is an expert in remote sensing, focusing on detecting accumulation rate changes and temperature changes over ice sheets using passive microwave satellite sensors. She has also studied the Greenland and Antarctic ice sheets on the ground using field techniques such as snow pits and ice cores. Her ground-based studies have included spending over 12 months in the Arctic and Antarctic to validate satellite measurements, and in today's talk, she will give insight into what it is like to conduct field research over the Greenland and Antarctic ice sheets during both the polar night and polar day, and on the meaning of her research results. NASA has graciously provided literature and handouts which are in the lobby, so if you're interested, please stop by to view them after the program. Today, please join me in welcoming Dr. Lora Koenig.
Great, thank you very much, and I want to thank everyone at the Library of Congress for inviting me here to talk today. And during this talk, I just kind of want to share with you a little bit about my research and how we do it and introduce you to the polar regions. So the first question that I always get in any of these talks is, why do you want to study snow and ice, and why do you go to these cold polar regions? And honestly, I don't really know. This is a picture of me circa 1980. I always loved the snow and ice. We had just gotten a few inches of snowfall in my hometown of Eugene, Oregon, and I found some skis, and I would be out skiing on the roads. And in my entire life, I have always loved to ski. I have always loved to be in snow and ice-covered areas. I also was inspired by NASA. I was inspired by the space shuttle missions and what our Earth looked like from space. And when I found out about remote sensing of polar regions, it just really fit with things that had always inspired me. This is actually a picture they call the Blue Marble. This is from 1972 from the Apollo 17 mission. And I always start my talks with this because this is one of our first complete pictures of Antarctica. Until this point in time, we really hadn't seen what Antarctica looked like very well, and it started to show us better mappings, and the satellites really, in the last 3 decades, have taught us a lot about the sea ice, Antarctica, and the polar regions. And you may ask, well, why do we really care about the polar regions? This animation, sorry, takes a little bit of time to start. Give it just a second, and it should start up. But the Earth's climate is really controlled by the oceans. And what this animation is showing is the thermohaline circulation. I know those are kind of big words, but basically it's showing the currents and the pumping of the ocean. And what you'll see is that the warm equatorial waters flow towards the poles. They become cold. The sea ice forms, excludes some of the salt, and the water becomes dense and it sinks. And it becomes, this is called deep water formation. Water flows towards, sinks off the coast, the east coast of Greenland. Then it circulates throughout the globe. It'll come down, it'll become the the Antarctic circumpolar currents when you come down to Antarctica. And what you can see is that the ocean, which really dictates our climate, is intimately tied with the polar regions. They truly are the refrigerators of the globe. We want them to stay cold, so this water stays cold and it continues to circulate in the ways that it has previously. The other reason the poles are important is because they're white and they reflect back sunlight. So this is called the albedo effect. And as the sea ice shrinks, we get more a darker Arctic, and more of the light is absorbed as opposed to reflected. Now think about, it's very easy when you're skiing to get sunburned. And that's exactly what this albedo effect is doing. So when we talk about the poles, in general, think, hey, we want them to stay cold, we want them to stay white. Well, there's been a lot of cryosphere in the news lately. What I'm showing here on the left-hand side is a recent melt event that happened this year. 2012 has been a very, very warm summer in the Arctic. What this map is showing is the red areas are showing melt on the Greenland ice sheet as monitored by satellites. And you'll see from July 8th to July 12th, there was this one melt event where we saw melt in the interior of in the interior of Greenland. As a matter of fact, almost the entire Greenland ice sheet experienced melt in 2012. What we know about this event is that this is the first time the satellites have seen it. The melt on the edge is very normal, but that has been increasing. So satellites in the past 30 years have been showing this increasing trend in melt. And again, in 2012, we have this record event where we've seen a larger melt extent than ever before. Simultaneously, the Arctic sea ice, and just right now, this image here was taken from 2 days ago, and it's showing the extent of the Arctic sea ice, which is actually monitored by the same satellites that can monitor this melt. And we see that the extent, we have 30 years of records, actually records since 1978, and the melt extent is going to be smaller than any other recorded year. So we're setting records. And again, what this does is it means that Greenland is continuing to lose mass, continuing to have more melt, and as the Arctic sea ice shrinks, we're not going to have as much reflectance, and we should expect more warming because of this. This graph here is actually showing the trend in what models predict for sea ice versus the red is what we've been measuring. And you'll see that what we've been measuring, we're having a decline in sea ice that is starting to be more than what the models were predicting. And again, the 2012 number is going to be lower than any of these other numbers that we've measured. So that's what's going on in the cryosphere. Hope it's not too bleak of a picture, but these are what we're seeing. We're seeing that both of our ice sheets, Greenland and Antarctica, we see that they're losing mass and temperatures are warming across them. Just to introduce you. These next slides will just give you a little background. The Greenland ice sheet is in the northern hemisphere where you have polar bears. It's about the size of Alaska and the Pacific Northwest in comparison to the U.S. Antarctica at the South Pole, it is about 1.5 times the size of the U.S. Remember, Greenland is a territory of Denmark, and there's about 50,000 people that live there. Most of them live along the west coast, and there's a few villages on the east coast as well. The Antarctic is run by an international treaty that is signed by a group of nations for peaceful and scientific research. When we talk about the ice sheets, there's one big question, and we've been asking this question since we first had those pictures. What's the size of Antarctica? What's the size of the ice sheets? And really, to understand the size of the ice sheets, what we need to know, this is a cartoon of an ice sheet, we need to know how much snow comes in, the snow accumulation, versus how much is lost, the ablation. How much is lost due to melting, snow blowing off, or just icebergs calving off into the ocean. And we want to know what the volume of this ice is. It's a little complicated because ice flows under its own weight. And I'm going to use this silly putty to kind of show you that. Okay, so if you get bored during the talk, just watch this silly putty. Think of this blue as cold ice and this yellow as warm ice. And I'm going to set them here. And you can watch them flow. And this is just like ice. It flows under its own weight. You can see the difference between how warm ice versus cold ice flows. So as this ice starts to flow, there's a very important point here that we call the grounding line. And the ice can flow and do basically anything it wants, but once it crosses this grounding line, it displaces sea level. And we want to understand how much ice moves across this line, because this ice out here has already displaced sea level, and the calving of the icebergs that have already been floating, that also does not change sea level. And the sea ice growing and shrinking every year does not change sea level, but it's when this ice flows past this point that it does change sea level. In this talk, I'm actually going to focus on snow accumulation, the input, because that's actually what I study. What are the predictions? People always ask. By 2100, we expect there to be somewhere the kind of a medium range prediction would be a meter of sea level rise. Maybe a little less than that, maybe 1 foot to 3 feet, or some predictions are higher than that. But what you should take from this map is the areas that are red are the areas that will be most affected by sea level rise. And this is showing what a meter will look like globally. There's a few things we know. We know for sure that as the Earth is colder, we have more ice stored in the ice sheets and sea level goes down. As the Earth is warmer, we have less ice in the ice sheets and sea level goes up. We're seeing warming at the poles where our ice is, and sea level will go up. We know that temperature and ice sheets are very tied. They change with the temperature, and I'll talk about this. We're trying to monitor very large areas, as you saw with the comparisons to the United States. And I do this in 3 different ways. Sometimes I use satellites, aircraft or airborne data, or ground research. What I'm showing here is how much we can cover in one season of data with satellite data, with air-based research, and there's a little tiny triangle down here. That's ground-based data. When we're talking about understanding what's happening to the entire ice sheets, we want to be working on the satellite level. But every now and then, and I spent probably the last 8 years working a lot at the satellite level, but the past few years I've been working down here at this ground-based level, and I'll show you why. Here's kind of what we do. Satellites measure some sort of voltage in space, or an instrument on an aircraft measures it. We compare that to some ground-based measurement, let's say a temperature. we develop some sort of equation that relates what the instrument sees to the measurement on the ground, and then we can make this equation, we can calculate the temperatures from the air, we can calculate the temperatures from the ground. As we get more satellite measurements or more ground measurements, we just keep cycling around here to make sure that our satellite measurements are comparing as best they can to the ground measurements. And so I'm always working in this cycle, and I'm really going to be talking to you a lot about, in this talk, about these ground measurements that we're going to use to come back up here to help calibrate our satellites. And I'll start talking about temperature. So there's one thing that we know about our satellites, and that's that most of our ground-based measurements have been taken in the summer. That's when you want to be on the ice sheets. You generally don't want to be there in polar darkness. And I decided that there is a summit camp in Greenland, and that I would go there for the winter and try and take some satellite calibration measurements, some of the first that we've really had. So this is just a picture of summit camp. This is actually the garage. Out here is the science building. This is the building that we live in. It's buried under the snow right now. And you'll see this flag line is being taken from the big house, and I'll show you some pictures. So that's just sort of a overview of what the camp looks like. And here's Summit as it relates. It's right at the very top of the Greenland ice sheet. It's also where the GISP-2 ice core was drilled, is from this camp, if you're familiar with that. And you say temperature. Well, why do you need to know the temperature? You can pick up your iPhone and you can ask Siri what the temperature is anywhere in the US and it'll tell you. But in Greenland, we really have a little more than a dozen temperature stations on the ice sheets, and those are marked here. Now remember, this is the size of Alaska and the Pacific Northwest. So these are the year-round automatic weather stations. There's not very many. A lot of times over the winter, they're only serviced in the summer, and over the winter they can lose data. The other way we can determine temperatures is with satellites. And satellites, we use infrared satellites to look at the temperatures. The problem with the infrared satellites are that if there's a cloud in between the satellite and the surface of the ice sheet, it's going to measure the temperature of the cloud. So we can only measure temperatures on cloud-free days. But I wanted to go try and take some more measurements in the winter. Here's what it looked like. This is the big house that I was talking to you about. That was the flag line. It's very difficult to take temperatures because, honestly, the wind is so high in some of the storms. What it'll do is it puts rime and blowing snow on all of the instruments. So even to get a temperature reading, we have to clean these instruments every single day to get a good reading. And here I have climbed the tower. These sensors are actually sampling the atmosphere, and then here we have some of the weather stations and the temperature measurements here. Not only does the snow in the winter hurt the temperature sensors, sometimes the temperatures can actually drop so low that it ruins the sensors. And people ask me what the coldest temperature I've ever been in. That's the coldest temperature I've ever been in. Here's the crew that we were there in with me in Greenland. There were 4 of us staffing the whole camp for the entire winter, so about 4 months. Here's myself, Bill, Kat, and Brad. Brad was the mechanic, camp manager, and then Kat and I were the scientists. And while we're there, we get to do our own science as well as other people's science. And I specifically talk about this research because it's a neat project where we took these instruments called thermochrons. And if there's any teachers in the rooms, these thermochrons are very easy instruments. They measure temperature, and you can use them in their classrooms, and NASA actually uses them in our education and outreach programs. And I said, well, we need to take temperatures across larger areas of space, and we need to do that in basically a less expensive way. And we have these new sensors. They're less expensive, but do they work as well as the more standardized NOAA? This is actually a NOAA temperature sensor. So I hung these little temperature sensors And I put the temperature sensors down on the ground as well because NOAA generally measures a 2-meter air temperature. And what the satellites measure is the surface of the snow. And so we needed to get better temperatures of the surface of the snow. So I put these temperature sensors out there, and I actually distributed them across space all over at the camp to see if I could measure temperatures and how those temperatures will, what happens with the temperatures and how they compare with the satellites. And this is what I want to show you in this graph. Okay, don't worry about all the numbers. This is a $3,000 instrument. This is a $30 instrument. This is the one-to-one line. So if they're measuring the same thing, the data should follow along that line. And what it says is within a few tenths of a degree, they measured the same thing. So there's a little bit of hand waving. We need to shield them from solar radiation and some things like this. But these temperature sensors did a phenomenal job. We were then able to look at the spatial extent of the temperatures across summit over the winter, compare them with the satellite measurements, and actually we saw that over the winter season, the satellite measurements seemed to be reading a little bit cooler than the actual temperatures on the ground. So temperatures on the ground were a bit warmer than the satellites. And we'll continue to get more of that data, because again, that's at one point in space, and see if we need to recalibrate how we use the satellite temperature records. While I was at Summit too, it was quite fascinating for me because I didn't only get to do my own research, but I got to maintain other people's research. We launched weather balloons to look at what the temperatures throughout the atmosphere looked like. We would go out on snowmobiles and measure the surface of the ice sheet so we could compare them with the satellite altimeters that measure the surface of the ice sheet. When we'd go out, we'd wear so much gear. I weighed myself once before and after, and I'd have 40 pounds of gear on because we'd be out all day in very cold temperatures. We also took radiometer measurements, and radiometers are instruments we have in space as well. I'd taken some of these same measurements in the summertime. I wanted to see how they'd changed in the winter, and we'd dig snow pits and look at what's called the brightness temperatures of the snow and see how that changes from winter to summer. The other thing we did a lot during the winter is we had to maintain the camp. So we dug a lot. What I'm showing here is that shop building. Here's Bill sitting up on top of the shop. This is after one of the storms. We had about 3 storms like this. You can see that all the snow drifted in around the shop door. But we had to dig this out. Here it is dug out before we could get out the equipment to help dig out the rest of camp. So anytime we'd have a big storm like this, we'd dig a lot. We also would eat a lot with all of that digging. This is one of our Thanksgiving dinners. People ask a lot about what we would eat. There's actually tons of food. You can see there's a lot of Cisco food. This is in a snow cave basically below one of the buildings, where it keeps all of the food frozen. And one of the greatest things about being on the ice sheets in the winter was the auroras that we would see most of the time. Well, the sun went down. It was dark for quite a while. And actually on January 28th, the sun came back up, but it was a cloudy day and we didn't see it. And we finally saw the sun again on January 29th. And we were there for about another 2 weeks before the planes came in to pick us up. Went back to my office, started looking at the data and preparing for my next trip, which would be in the Antarctic summer. It would be in, I left in November of 2010 for what we call the Satellite Era Accumulation Traverse. So we went to Antarctica, went to West Antarctica here. What we were specifically looking at was snow accumulation. Again, how much snow is falling on the ice sheets. Here's the team. This is the 2011 team. We were there in 2010, 2011. I'm going to point out Ludovic Broker, who's actually in the audience today, who helped us. But we were a team of, there were actually 6 of us, and 5 went on the Traverse this season. I'll show you, this is the LC-130, how we get out into the middle of Antarctica. It's on skis, These are operated by the 109th Air National Guard out of Schenectady, New York. And they take us out to our research sites at this camp. And this camp is actually Bird Camp in West Antarctica. Why do we want to study accumulation? So we know that the globe is warming. We know that the polar regions are warming. With that warming, what we expect is there to be more precipitation. So think in general, a warmer summer storm has more rain than a winter storm. And there have been many projections that there will be a 10 to 20% increase in the polar in the polar regions due to this warming. But an increase in precipitation has not been observed to date. There's a few reasons for this. Think about when it snows at your house. If anybody was here for Snowmageddon, I don't know if you were, but I was. Our front door was actually in an area where the wind was scouring it out, so we didn't have to dig too much. But in our back corner of our house, the snow had piled up, and it was very high. And if you think about the variability just across one snowstorm that you see, and think about having to measure the amount of accumulation across an entire ice sheet, it's very, very difficult. The way snow blows, it precipitates. In Snowmageddon, we got more snow than our friends in Alexandria. And understanding precipitation, it takes a lot of measurements, and it is quite difficult. So on the ice sheets, this is showing how precipitation is preserved. So here we have snow that's falling, and it forms layers. And it'll stop. This is zooming out to the full depth. And you'll see that each time it snows, a new layer is formed. Think of this like tree rings. And what we can do is we can go and we can take an ice core of each of these layers and see how much accumulation fell. That tells us what the accumulation was at one point in space. Now here's what it looks like. This is some footage of Randy actually sending our ice core drill down. We use a quick and rapid ice core drilling method. There's a lot of manual work, but you'll see, so the drill went down into the ice sheet. The actual ice core, you can see it actually just coming out the bottom, is inside the core tube. We plunge it out onto the core handling station, where it'll be weighed, measured, and packaged to go back to the labs. So in this ice core, we've taken a sample of that history of accumulation. Here's just some more pictures of how it works. A lot of times we have to drill from the bottom of a snow pit, and when we do that, we actually sample this snow here into little bags and take it back. But that snow won't actually stay consolidated enough, so we might lose it. We don't want it to break up because we need to keep this history intact. So we drill once the snow has become compact enough that it'll survive the shipment back to the lab. Again, here's a picture of us measuring these cores. And then the cores are put into these tubes to preserve them. They're labeled so we know where they are from, and they're put into a box and shipped back. There's a very important process in this. We need to know what is the top and what is the bottom. Can anybody tell me how we know what's the top of the ice core and what's the bottom? The arrow. The arrow points to the top, and there'll be arrows written on the tube, and so we always know the chronology of the cores. So here's a core. You're looking back in time. This is looking down the core hole. The cores that we take are quite shallow. We are looking at the satellite era, just the past 30 to 40 years. Other ice cores can go back hundreds of thousands of years. So these are very shallow, but we're really looking for that. As the temperatures have increased, we know the temperatures have been increasing on both poles during the satellite era. We want to try and measure that accumulation increase during that same time period. So ice cores are kind of tried and true way of measuring accumulation, but we have these new sensors. We have new radars. They're called near-surface radars. These ones were actually developed by students at the University of Kansas, the Center for Remote Sensing of Ice Sheet, and they just do great work there. And they develop these radars. What they do is they image those layers in the very surface of the ice sheet. So we can use these radars to connect the cores and give us a broader spatial example of what's going on. Now this animation was actually made for another one of our missions, but I want to show it to you. Focus on the gray line. The gray line is what we're measuring. Just so you know, the green line is altimetry. It measures the surface of the ice sheet. We have other instruments that measure radars that go down to the base of the ice sheet. But what we're looking at is this accumulation area. What's happened in the past 30 years. And these radars will penetrate and sample, give us a 3D view of just that surface of the ice sheet. So that gray radar line, that's what we're looking at. And here's what our traverse and the data looks like. This is all actual data. Our visualizers have made this. Now you'll see that the exaggeration is going to come up quite a bit here. But here we are traversing across this divide, and here's our radar data, looking down into the ice sheet, showing us all these layers. The little blue lines are all the ice cores that we drilled. And this is called an ice divide. It's towards the Amundsen Sea on one side and towards the interior of the ice sheet. And we have higher accumulation on this side and lower accumulation as we go to this side. So this is a really good area to study accumulation on the ground. And you can see the layers. It's a little difficult on the screens, but you'll see all the layers. And this is what our actual data looked like on the traverse that we did, traversing across Waste Divide. And again, we're looking down into the ice sheet. So here's the data. And what we're seeing here is you can read this sort of like tree rings. Each one of these is a year. So this was taken in 2010. This is a snow from 2010. This is a snow from 2009, 2008, 2007. We had ice cores at either side of this. Actually, core 10-3 ended up being a little shorter than 10-4. And the reason for that is you'll see that core 10-4 was in a higher accumulation region. There was more snow. The way you can tell that is see how the layers are closer together here, and then they start to dip. You can really see it here as we go into the higher accumulation areas. So what we can do with the radars is we can trace these lines. We know what dates they were from the ice cores, and we just took our measurements from our ice cores that told us what accumulation was like at just one point, and we're able to connect them and see what accumulation looked like across this line. And this is the sort of data that we really need to compare with the satellites. And what we learned from the ice cores, and this was a very surprising result. What I'm showing here is we've stacked all of our ice cores together, so there's actually a stack of 5 ice cores here in that region, and we see that in this one region of West Antarctica, where again we were expecting to see an increase in accumulation, from the 1970s to 2010, you'll see that this line is going down. We're actually seeing a decrease in accumulation in this one area. Now, during this time period, when people talk about general climate trends and then variability, there was an anomalous low pressure system that sat in the Amundsen Sea, and that probably redirected some of the storms out of this area. And so we actually, where we're expecting to see an increase in accumulation, we're seeing a decrease. And it just shows the complexity in measuring this, and that we'll need to continue to take more measurements across space to really look at this. And what this would also mean then is we really want to measure that accumulation increase, because that would help offset some of the sea level rise. I'll also say that some of our satellites, the GRACE satellite, showing mass change, was actually showing a decrease in mass in this area, and that's probably from both ice flow as well as a decrease in accumulation. So every day a new fact comes to life. And as I tell you a little bit about this Antarctic traverse, I thought I would compare it with some of Scott's photographs, because the Scott Amundsen traverses actually occurred 100 years before our traverse. and people ask us what it was like. So here's the Terra Nova going down to Antarctica, and it took them months. We actually get to Antarctica on a C-17 airplane. It takes a few hours. It does seem like months when you take the flight to Christchurch, New Zealand from Auckland, Auckland to Christchurch, usually from the US. And that's, 12 or 14 hours in flight. But once we get to New Zealand, it's about a 4.5-hour plane ride. We land outside of McMurdo. You'll see this plane has wheels. It lands on the sea ice outside of McMurdo Station. When we head into the field, the photographs actually don't look too different. Here's the Scott expedition. They're all sleeping. Well, we do the same thing. Here we're in a C-130. You can see we've loaded up our snowmobiles for the traverse. All of our sleds, all of our gear is loaded here on pallets. Myself and the load master are more senior people on this traverse, so we have taken the best sleeping areas of the snowmobile seats, where the students are stuck here in the jump seats. And I love this picture because here's a picture of Landon with his iPod. And that's actually a relatively large iPod, judging by iPods this day. Well, on the Scott Traverse, they also had music, but their music was much more difficult. And I'll also say that they got to have dogs in there. There are no longer dogs allowed in Antarctica. Well, everybody seems to take the group photos. They don't look too different before you set off. And actually, when we set off on the traverses, there's quite a lot of similarities. I mean, they're using ponies and we're using snowmobiles, but we all are carrying our sleds. And I love that our last sled would be the radar sled that's gathering our scientific data, and sitting right up here on top of it is the GPS antenna telling us the height of the surface of the ice sheet, as well as exactly where we're recording our data. Well, on the Scott expedition, this little wheel here is also measuring their distance, and they're taking their scientific measurements here on this sled. This is one of Scott's campsites, outside of McMurdo on the Ross Ice Shelf, and you'll see what we now call Scott tents, these pyramid-shaped tents. They have some skis and some flags. Here's a picture of one of our camps once we're out on the traverse. You'll see that we still use the same Scott tents. Those Scott tents are really our best safety mechanism when storms come. They are just bomb-proof, and during storms, windstorms, you'll get into the Scott tents because we know that they'll survive the storms. However, they're a little cold. You can cook in them and warm them up, but there's a lot of space in them, and then they're quite cold. So a lot of times we prefer to sleep in these new mountain tents, but these mountain tents will always have a couple extra spares of them because they can be completely shredded in the Antarctic storms. And we have some flags too, just like Scott. Anyone know what the flags are for? They're green flags. Are there any guesses? This is our water mine. Bathroom flags will be yellow or black, so you don't go near them, but the green flags mean go, and you'll see our little shovel here where we're digging our water. Well, Scott would cover up his ponies every night. We cover up our snowmobiles every night. You want to make sure everything's well secured if any storms were to come through. And this is one Scott, kept great journals, and he wrote all of his journals. And actually, Scott Polar Research has digitized his journals, and it's great. You can go there on the web and flip through them. Well, no one will ever have to digitize my notes. All of our notes are generally taken on the computer at night. People ask me the coldest I've ever been. This is the coldest job right here. When you're outside digging, you're generating heat. When you have to sit and write your notes and your fingers are exposed, it's very cold. But all of our data now is digital, so that's quite a difference between now and then. Here's Ponting, who took a lot of the photographs from the Scott expedition, and the cameras have certainly gotten a lot smaller. Here's Randy taking pictures of penguins for his children, where we are in the middle of the West Antarctic ice sheet. Penguins do not go there, so he brought along some of his own. And again, look at the size of the camera. I mean, we have cameras in our pockets all the time. I'll also just mention that this is at what we call now Bird Surface Camp, because Bird Camp was a International Geophysical Year camp, and that's now buried below, because this is the accumulation area of the ice sheet. So that camp is actually buried below this, so we call this Bird Surface Camp. But this is actually the bathhouse, so there's some warm water in there. You can take showers at the camps. People always talk about what we had to eat, and I love this. We had 3 pemmican meals left and decided to make them 4. Tomorrow lunch must serve 2, so we reduced rations tonight. This is from one of Scott's things. And pemmican is like a fat, like kind of eating butter, like a fat and protein stick. We eat a lot better than that. This is actually the food that we packed for the traverse. We usually will come back with over half the food that we take. We overpack so much food. You can see there's Lucky Charms in here. There's couscous. We can take meat, anything that says frozen, cheese. And we go look at some of the Scott rations at Hut Point, and here's some of his rations. But we just go to look at them, and we eat quite well on these traverses, and we don't go hungry. The other main difference between traverses of today versus the earlier traverses is that we use GPS, and I use this is actually a picture from Greenland, but I use it to make the point. Here I'm surveying drifts with a GPS unit on my back. When we do traverses in Antarctica, our GPS tell us where we'd go. We would be completely lost without them. They're one of our main safety devices. You will always have extra batteries in your pocket to stay warm, and we rely completely on GPS. And I think all of us would not survive very long if we had the tools that the earlier traverses used. One of the things that Scott said is, pray God the wind holds tomorrow. And we still do have storms. That hasn't changed much. The storms out on the ice sheets can be severe. And are cold, blows a lot of the snow around. So here's one of the pictures of the storm from the 2011 traverse. But if you're in the summer, the sun will always come out. And again, I put this in here to acknowledge Ludo and all the work that he's done with this traverse as well. And so the sun will come out, and that would be unless you're in Greenland, because when it's summer in Antarctica, it's still going to be winter in Greenland, where it'll be dark. And I'll just kind of end my talk here by saying I hope I showed you a little bit about the research that we do on the ice sheets, how we're on the ground really getting measurements to make sure that what our satellites are seeing are as accurate as possible, so we can look at these long-term trends over the ice sheets and the Arctic sea ice, and be confident in the predictions that we make into the future. And again, what we're seeing over the ice sheets really is that both Greenland and Antarctica are showing mass loss. There's certainly more warming going on in the Arctic, and we'll continue to see that, and our satellite trends are continuing to show that increase in melt and the decrease in the Arctic sea ice. If you want more information, especially about just the field work, check out the blogs that we've done at NASA Earth Observatory. NASA has this great visualization app for your iPads. There's a lot of snow and ice related stories on there with images. Check that out. You can always Google NASA Cryosphere or follow us at NASA Ice on Twitter. And with that, I'm happy to take any questions. You can You can also look at the flow of the ice sheets, and you'll see that the warmer ice has splurged out a lot more than the colder ice. It's flown. It had faster flow.
We will have comments and questions now. I will just ask Dr. Koenig to repeat the questions so that they can be captured accurate. Okay, well, for the webcast. And I wanted to start with a question about the difference between warm ice and cold ice.
Warm ice, the main difference between the warm ice and the cold ice that we use in the models is to really show how fast it's going to flow. So the warmer ice will generally flow faster than the colder ice. Yes?
What is the temperature difference between the two kinds of ice? How much difference is there?
Oh!
When you say warm and cold,
You know, yes, warm and cold. It's you know what? I don't know the exact differences. It's degrees. You know, tens of degrees.
Have you been able to measure the same sort of melt events in Antarctica as you have in Greenland?
Yes. So the satellites. We'll start with the satellites. The question was, have we been able to measure the same type of melt events in Greenland as in Antarctica? And the satellites show when liquid water forms somewhere in the top few meters of the ice sheet. So the satellites that look at Greenland and Antarctica can both measure that if there's liquid water there. What we see in Greenland, it is warmer, and around the perimeter there is melt every year. The melt frequency around the edges of Greenland, and you'll see lakes form on the surface of Greenland. That melt happens every year. As we get into the higher interior of the ice sheets, that's where melt is less common. So, for instance, in Greenland, we saw this melt event that covered the entire ice sheet. We have not seen that in Antarctica. We don't expect to see that. Part of that is because East Antarctica is much higher and much, much colder. So we can measure the melt extent, and you can look online. There are some maps that will show the melt extent in both Antarctica and in Greenland. In Antarctica, it's not that large, just a few areas around the edges of Antarctica. Out on the Antarctic Peninsula, there's melting. But the melt extent into the interior of Antarctica has not occurred.
it seems like technology is driving the sensitivity or quality of the data that you're receiving. Can you address that, how technology has changed over the years?
Yeah, so the question is how technology helps increase the accuracy of our measurements, right? And yes, what technology I think has done, there's a few things. Technology has given us much more accuracy, especially with the GPS systems. We can calculate the position of, say, a laser altimeter that's going to take the surface height of the ice sheet much more precisely, and that's, since the 1990s. So that increased our accuracy. We also have these new radar instruments, which are giving us better spatial extent. And I think more than anything, the technology now is really helping us to increase the spatial extent of our measurements, where before we had to take ice cores, and now we can really monitor large areas of the ice sheets from aircraft, and it gives us from the ground or from aircraft. Those same radars can be used on aircraft, and that gives us a much better spatial picture of what's going on. So I would say that technology is helping, and it's giving us more data over larger areas of space. Yeah.
Where are the ice cores stored?
The ice cores. So our ice cores, like I said, they're what we'd call shallow ice cores. They're 20 meters, 50 feet or so into the ice sheet. So those ice cores actually went back to our colleagues at Brigham Young University, and they're analyzed in a lab there. They are not super important ice cores because we can go re-drill 5 of them in one season. There is the National Ice Core Laboratory in Boulder, Colorado. So one of the camps that we worked out is called Waste Divide Camp, which is in West Antarctica, and that's where the U.S. is leading a drilling effort. They've actually completed drilling the core. And that goes all the way to the bed of the ice sheet. So, miles down. Those ice cores are more like national treasures. They're stored, and that ice is stored in the national facility. Yeah.
I've heard that with the latest Russian drilling in Antarctica, there's some concerns about pollution or contamination because of the diesel they use. Can you speak to that?
The question is about concerns with the Russian drilling into Lake Vostok about contamination of the lake. And I don't know a lot about that, but what I can say is that when the drill goes down, first, some of the things that people don't know a lot about is that there's water underneath the ice sheets in many places, and Lake Vostok is one of the largest lakes, but there's a lot of little lakes underneath the ice sheets that fill and drain, and it's still one of the large research question that people are looking into, and that people don't know. There's a lot of water under the beds of these ice sheets. Lake Vostok again is one of the biggest, and last season the Russian team did drill in and hit the water, but beyond that we know they drilled into the lake, and we don't know much beyond that. They do use a drilling fluid, diesel, or there's different chemicals that they use, and what that does is it keeps the hole open, so you can continue to send your ice core drill down, because if not, the ice would flow back in and close up the hole. So they use the fluids to keep it open. But beyond that, I think we'll hear more and more about that in the upcoming years.
You
Yes.
commented a lot about the ice sheets during the summer. I was curious if you have any comments about what happens to like sea ice during the winter, especially something like happened this past year up in the Bering Sea, where the ice sheet was covering more of the Bering Sea than any time since 1972.
See, and I don't know a lot of the specifics. The question was about Arctic sea ice and it actually extending into the Bering Sea. So again, I don't study the sea ice specifically, so I don't know about that specific event. But it is natural for the Arctic sea ice to shrink and grow every year, and I would recommend going to the NASA visualization. They have images of the satellites showing that, how it grows and shrinks, and it's pretty dynamic in that way. And again, I don't know about the specific event of it growing into a different area. The ice pack does shift around, and that's relatively natural. Here.
Do earthquakes have any impact on the shift of the ice at the low levels?
Do earthquakes have effect on the ice, like the ice movement?
Yes.
So the question is, I do not know that, but I do know that people measure on the ice sheets they have what's called ice quakes, where when you have calving events, which are when the glaciers calve and things like that, you can actually start to measure that. But on the broader impacts of does an earthquake relate to ice flow, I don't know. Yes.
Is there a hypothesis for why the precipitation has not increased in Antarctica the way that computer models have predicted?
The question is there a hypothesis on why the accumulation has not increased like the models have predicted? And right now, I think our main hypothesis is that it's probably increasing, but it's shifting around. So we don't know. Right now we're saying that our measurements are probably not good enough. and that we still expect it to happen. Again, it's warming in the very simplest of physics. We should have an increase in accumulation. And a lot of us, we really want to see that increase in accumulation to help offset some of the sea level rise. Our measurements with the radars are getting better, but it's probably an undersampling issue. Any other questions? Great.
If there are no more questions, we'll conclude our program, and thank you for joining us today.
Yeah. Thank you.
Thank you.
This has been a presentation of the Library of Congress. Visit us at loc.gov.